Hey there. So today we're looking at section 2.2, which deals with properties of water. So this is building upon what we did in 2.1 in regards to continuing to talk about biochemical kind of basics, right? So atoms, ions, molecules. We look at water. Water is an example of a type of molecule because it has within it some covalent bonds, and we're going to look at where those are found. But in addition to that, water is pretty unique in that it will it allows life forms to exist in certain ways that, for scientists, we tend to believe that that wouldn't be possible if it wasn't for some of these unique properties of water that we're about to get through and talk about here. Okay, so go ahead and put down the heading for me, section 2.2, properties of water. So the objectives for this first section, or I guess for section 2.2 here, the second section, explain the unique properties of water, explain how water's polarity affects the way water interacts with other substances, and the last one, explain why buffers are important to the survival of an organism. And buffers are something that you might remember having heard about in the past, especially when you did some chemistry, maybe in 7th grade or 6th grade. But if not, we're going to spend just a brief amount of time on buffers. The majority of what we're going to do in section 2.2 here is going to be involving those first two objectives at the top. Okay, so looking at the molecular structure of water, and I would go ahead and get both the heading here and the bullet that you see there. So water molecules are something that we call polar, and that doesn't mean that they are cold. This really has no reference to this idea of the North Pole or the South Pole. When we talk about polarity in chemistry, this has to do with charges and distribution of electrons, really driving the formation of some partial charges that we see in certain types of molecules. And water is an example of a molecule where we have a good amount of polarity. What that means is that we end up with a molecule that has some slightly charged areas, and as a result of that, water becomes really good at doing things like providing the solvent to create solutions, and we'll talk about what that means here in a few slides. But we mentioned in 2.1 that ionic compounds, being that they are fully based on these attractive charges between positively and negatively charged ions, I mentioned that those are really good at dissolving in water. And the reason for that is because water itself has some slight charges. Now, water is not an ionic compound, but within this molecule, as you can see here, our distribution of electrons is kind of driving exactly how these charges form. So when we look at this molecule of water here, okay, what you see is what we would have looked at in 2.1 when we were first talking about different types of bonds. So you can see oxygen, remember, is atomic number 8. So maybe not an equal sign there. Let's say oxygen, we could say if we were doing our element diagram here, our symbols from the periodic table. Oxygen is atomic number 8, and its atomic mass is usually 15.99, so we often will just round that up to about 16. So if we count the electrons that actually belong to oxygen, right, if there's 8 total, right, we know that we can fit 2 in the first, so here's 1 and 2, and then the remaining 6 have to fit in the second energy level. So here's 1, 2, 3, 4, 5, and 6 to get to my 8 total. Now the ones that I'm obviously leaving out are these two right here because I'm assuming in this case that those are actually belonging to hydrogen. So what we see happening in this example where we have a molecule of water of H2O, right? We have 2 hydrogen atoms that want to interact with a single oxygen atom at the same time. And what happens there is we end up in this beneficial type of scenario where oxygen now kind of has 8 outer electrons. It satisfies its octet rule, in meaning that it's got kind of 8 there because it's going to share the electrons that hydrogen is providing for this relationship. Hydrogen, remember, is atomic number 1. It's the very first element in the periodic table. It only has 1 proton and 1 electron. And as a result of that, because it's so small, it still kind of wants to fulfill the need of filling up that first energy level, which we know can accommodate 2 electrons. So because there's only one there, hydrogen is a great electron kind of donor or acceptor, or even in this case, a great example of a sharer in the formation of a covalent bond. So what we get in this molecule of water is a covalent bond that forms here and a covalent bond that forms there. And remember, each of those bonds contains a pair or 2 shared electrons. Okay. Now, what makes water polar is actually based on how the atoms in this molecule are sharing pairs of electrons. All right. And so what we mean by that is, if you just look at the scope of this picture, oxygen is gigantic compared to the hydrogen atoms, right? I mean, it's significantly larger. I feel like you could fit probably 6 hydrogens in the diameter here of the oxygen atom as we look at it. So what that means is that oxygen, being that it is so much bigger, we say it has a higher electronegativity, which means it's going to pull the electrons here from my hydrogens, the ones that are even being shared, okay, in that outer energy level of both. It's going to pull those closer to its nucleus, because remember, in the nucleus of oxygen, I have 8 protons. I have 8 positive charges there, and those 8 positive charges are going to draw towards them these negatively charged electrons. Hydrogen, in comparison, only has 1 positive proton here in its nucleus, and so the attraction there is not going to be nearly as strong. Okay, and we see this with lots of different types of molecules that are different, drastically different in size. All right, so water is considered polar because, again, we're not sharing electrons equally. All right, that would be something good to jot down. So when we look at the structure of water, what makes this really, really important in the formation of the fact that this is going to be polar is that we now have these opposite charges that can then interact between water molecules. So these are what we call intermolecular forces. All right, so it's intermolecular. So inter, remember, meaning differ. So we're talking about 2 different molecules. They don't have to be different in the form of like they're made up of different atoms. They can still be 2 water molecules. But we're talking about now interactions between separate molecules, not within a molecule, but 2 separate. So one of the bonds that happens to be formed through these types of interactions is called a hydrogen bond. And this is the 3rd type of bond that you need to know in this chapter. So remember, in section 2.1, we did covalent, which is shared pairs of electrons, very, very strong. Ionic, which is not so strong, not sharing pairs of electrons, but is instead like this attractive force between a positive and a negative ion. Hydrogen bonds here are even more weak than ionic bonds. This is an attraction between a slightly positive hydrogen atom and a slightly negative atom, usually oxygen or nitrogen. And in this scenario where we're looking strictly at water, it's certainly going to be oxygen. Okay, the symbols here that you see in this diagram, these that are like, they look kind of like 8s that aren't finished, or S's with a tail, those mean slightly. All right, so when I say slight charges or slightly negative or slightly positive, we can't just represent those in chemistry with just a regular, positive or negative symbol. You have to include something extra so that someone who's viewing this and learning about this understands that this is not a full ion, right? We're not gaining or losing electrons. We're just not sharing them as equally as we could be, okay? So hydrogen bonds by themselves, like I said, are very weak. They're going to be weaker than ionic bonds. They certainly would dissolve in water, as water is also made up of these. But again, these are just these slight kind of attractive forces. When we look at a solution of water or a large quantity of something where we see a lot of hydrogen bonding happening, together they can kind of work together and make their strength more powerful, if that makes sense. So we see in molecules like DNA, hydrogen bonds that are actually holding together the sides of that DNA ladder, the double helix, as we'll talk about here in a little while. So within DNA, you imagine how important DNA is as a molecule. These things are what we use to hold it together. So they certainly can play an important role in living things, and they certainly do when we talk about solutions of water. Okay. So as we go on, and again, definitely make sure you have this information on this slide. That is a vocab term. You definitely want to know hydrogen bonds. So this is just another way of representing the interaction between multiple water molecules in kind of the same solution. So if we have a solution, obviously we would have more than just 5 water molecules in a solution. But when we look at a solution of water, the same things kind of apply. You can see here we've got covalent bonds here, represented by those single kind of connected lines. So these are covalent, where we're sharing pairs of electrons. So those are very, very strong. And then between these different, electronegativities, between these different partial charges on these oxygens and hydrogens, we get the formation of these, I'm trying to draw these slightly negative, slightly positive, formation of these hydrogen bonds. All right, so if we draw some of these and label them appropriately here, what we can see is we get hydrogen bonds here, we get a hydrogen bond here, we get a hydrogen bond here. So anywhere that we have these slightly opposite charges, we end up forming hydrogen bonds. So again, the hydrogen bonds are between different molecules. The covalent bonds are what are actually holding together an individual water molecule kind of on the inside. Okay. So all of this ties in with this idea that water is a polar molecule because it does not share its electrons equally. And if it sounds like I'm repeating myself, I am, because it is important. Okay, so make sure that you're kind of getting the gist of that here. So what we know about water in terms of how it's important for living things, we know that the structure of water, the fact that it's polar, the fact that it forms these hydrogen bond kind of networks within a large volume or quantity of water, all of that leads to some important properties. And there are more than 3, but we're looking at specifically 3 here on this slide. 2 of these are vocab terms, so definitely make sure you get those. And then the last one here is maybe the most complicated one. And so I'll explain that one in a little bit more detail, all right? But the first one that we're looking at here, the first property of water that we know is important for living things that deals strictly with the composition of water is something called cohesion. And if you remember from Latin, co was a Latin root that meant both or together. So this is the attraction between molecules of the same substance. This is how they interact with each other in that substance, okay? So this is working together for a common goal. And with cohesion, what we tend to see is things like surface tension that occur. So if, for example, if you took a penny or any kind of coin and set it flat on a table and then dropped water onto that penny, what you would end up seeing is that the water actually, if this is my penny and this is my kind of flat level, the water will actually kind of bubble up on top of that surface. Okay, now depending upon how quickly you drop it and the force of those drops, that'll kind of determine how much you can fit. But this is a lab we routinely do in class, and it's interesting because what students find is that they always fit more on that penny in terms of the number of drops of water than they would have ever expected. I've had kids that fit 60 drops of water on a single penny, which is definitely a significant number. So that's something that we call cohesion. It creates a surface tension property that allows things like, for example, the insect that you see here on the screen to be able to walk on water. So you can see where here the their legs are being supported by the surface of this water that's kind of tense around them, right? It's kind of bending to support the weight and the mass of their body. So it's kind of cool. The second type of property that we're looking at is called adhesion, and this is almost the same as cohesion. The key difference is that we're looking at, this is now attraction between different substances. Okay, so this is not water being attracted to water. This is water being attracted to other things. And water, we know, is a great is great at attracting to things, especially like glass, where we might see some charges there. And so where we see that specifically, if you've ever had to measure the volume of water in something like a graduated cylinder, if you fill up water in a narrow glass tube like that, right, what you see is kind of that concave dip, okay, that forms. And that's formed because water is being drawn up the sides of that graduated cylinder, and then it kind of dips down to its natural level where it actually should be in terms of its volume, kind of in the center. So when you go to measure the volume of a liquid like that in a graduated cylinder, you've been taught, hopefully, that you kind of place that at eye level and you check it for the base of that kind of concave, what we call a meniscus in that structure. Okay. So adhesion is just that, it's water attracted to other things. Heat capacity, this is also sometimes called high specific heat, and I'm going to jot that down here just in case you feel it necessary to write that. I don't know in which way this will be phrased on a test, quiz, EOC. Okay, so it may be helpful to jot that down. But one of the important things we know about water is that water is really great in terms of resisting changes in temperature, and that has everything to do with these hydrogen bond networks that we form in large quantities of water. So when we look at it like at any type of liquid, at any type of heat capacity, that's defined as the amount of energy we need to increase a temperature by making molecules move around faster. And if you've ever tried to make macaroni or ramen noodles on the stove, right, you fill up a pot with water from the tap or from wherever you're going to use it, and you set it on the stove and you turn on the burner and you turn it up to high, right? And if you're like me and you wait and you make it at maybe the most the latest possible time, you're of course hungry when that happens, and it seems like you have to wait forever for that water to start boiling, right? Usually it's 5, 6, 7, 8, 9, 10 minutes, depending upon the strength of the energy coming from your stove to start heating up that water, and also the quantity of the water in the pot. But once it's heated up, right, it finally starts boiling, you can add the pasta and it will cook the pasta, right? Well, water is great in that regard, in that it resists those changes in temperature. If we were cooking with any other type of liquid, it would not take nearly as long as it does to take water to get up to that boiling temperature, that boiling point. And what that means is that for our cells, this becomes really, really important. We are constantly inundated in our cells with chemical reactions that are releasing tons of heat, tons of energy, tons of heat. And if it weren't for this kind of temperature resistance quality of water, our body temperatures would be fluctuating all of the time, and we know that this doesn't happen. So this idea that water has what we call a high specific heat, or a very high heat capacity, allows us in our bodies to maintain what we talked about earlier, which is something called homeostasis. So this has everything to do with maintenance of constant internal conditions in the body and in our cells, and specifically in dealing with things like maintaining a body temperature. Okay, we don't want our cells to increase in temperature too quickly or to change temperature too often, because then that runs a risk of endangering things like our proteins that need to do the work of our cells. All right, so it's very, very important that we maintain constant temperature, and we do that with the help of things like water. Okay. So those are some of the unique properties of water. One of the other things we need to look at is exactly how water plays a role in formation of things like solutions. So a solution is something that certainly in chemistry you would have learned about, but we also have solutions that are important in living things. And when we talk about solutions, we're dealing with one substance that's actually dissolving into another substance. So in this example, we have sodium chloride. And if you remember that from yesterday, that's kind of the fancy chemical term for salt, right? The thing that we add to food and that we bake and cook with. So when we add salt to water, if you've ever done that before, you know that salt readily will dissolve in water. And remember, the reason for that is that salt is an ionic compound. It's happy to kind of fall apart and start interacting with the charges of water as a polar molecule. So those slightly charged regions of water are happy to start interacting with the negative chlorine ions and the positively charged sodium ions. And we can see that happening here. So you have molecules of water now that are interacting with sodium ions. You have molecules of water here that are now interacting with chlorine. And what ends up happening is you no longer can separate salt from the water in which it's dissolved, right? That's what we have. So we call a homogeneous mixture, or in this case, a solution. Okay, so definitely make sure you have the definition for solution. When we look at formation of solutions, we can also define some other terms, which would be solvent and solute. So notice the only thing that I've done on this slide is I've just added these 3 items. If you got the first 2 with the last slide, you do not need to rewrite those here. So a solvent is what we're going to be using to dissolve a solute. All right, so solvent by definition is something that we have more of. It's present in the greater amount, and its primary job is going to be to actually dissolve the solute and create our solution. So the solvent I tend to think of as always being liquid. If we're going to make a liquid solution, I hope you have more liquid than you have solid, right? If you're talking about making Kool-Aid and you just have a whole bunch of sugar, but like a teeny tiny amount of water, well, you're not going to get Kool-Aid. You might get some weird little paste, and it's going to be super sweet and probably hard to consume and digest. What you need is a large amount of solvent in the form of liquid and water, and then you need your solute, sugar, to create that solution, that drinkable Kool-Aid. So a solute by definition is what dissolves into a solvent, and it's present in the lesser amount, meaning we have less of the solid solvent, or sorry, less of the solid solute than we have of our liquid solvent. And our solute, by the way, doesn't have to be solid, but in the examples I'm going to look at with you here in a second, it almost always is a solid type of compound. And if not, it's certainly present in the lesser amount. Okay, when we talk about creating solutions, the amount of solute determines what we call our solution's concentration. In general, the higher the solute, the higher the concentration. Okay, so that doesn't mean we're talking about like your ability to focus on something, right? Concentration is certainly just representing how much of something is present. So the higher the concentration, the more solute we have in these scenarios, okay? So let's look at a couple of examples, and I do want you to jot these down as I write these here on the screen with you. So let's say we want to make, let's go back to one of the examples that we just talked about. Let's say that we want to make salt water. All right, and so obviously the components of salt water are pretty straightforward, right? It's water and it's salt. It's the 2 words that make up what I'm trying to make here, right? So the way that I make salt water is I'm going to add salt plus water, and I get salt water. Look at that. All right, so if I'm adding salt plus water to get salt water, let's identify what some of these items are. We want to pick out what's my solution, what's my solvent, and what's my solute. So I'm just going to box in the ones that we identify with some different colors here. So hopefully that prevents me from having to write a whole bunch more down here. All right. So in this example, my solution is going to be my product, right? That's going to be the scenario for really all of these. So my salt water is going to be the solution that I create. Remember, when we talk about these solutions, what we're using to dissolve our solid component, what we're using to dissolve our solute is going to be what we call our solvent. Remember, we have to have more of our solvent than we have of our solute. So if you look at the 2 options I have left, well, let's think about what we want more of if we're going to make salt water, right? Do we want to have more salt? Do we want to have more water? And the answer is certainly going to be we want to have more water, right? Because we want this liquid solution when we're done. So my solvent in that case becomes water. That means my solute, the one that's present in the lesser amount, the one that will dissolve in my solvent of water, is going to be salt, okay? Let's look at another example. Let's say we want to make sweet tea. And if you've never heard me say this before, I am not from the South, and sweet tea is not my thing. But sweet tea is something that I know is a lot of other people's thing, and so we'll use that as our example. So sweet tea, the way that we make it, the way that I understand it, the way that it's always told to me when I ask this question in class, is you take unsweetened tea, or you brew your own unsweetened tea, right? And which is essentially water that's been flavored, kind of like coffee is water that's been flavored. We're going to add to that sugar, and we're going to make our product of sweet tea. So I'm going to say here for my components of this, I'm going to say I have unsweetened tea. So unsweet tea, and I'm going to add to that sugar, and my product is going to be sweet tea. How about that? Okay, so again, if we kind of work in the same direction that we worked with on the last one, my product is the same as saying my solution. So in this case, my solution, what I want to make, my end goal is sweet tea. The sugar in this case, you want to think about again, what do I want to have a larger quantity of, right? Would I rather have a whole pile of sugar with a tiny, tiny bit of unsweet tea? Or would I rather have a whole bunch of unsweet tea and then a smaller amount of sugar to add in? Again, the question becomes then, do we want a liquid solution, or are we creating something else, right? And in this case, we want a liquid solution. So that means that my liquid has to be greater than my solid. So that makes my sugar in this case my solute. In my unsweet tea, the thing that I need in a greater amount, the thing that's going to actually dissolve my sugar, is going to be my solvent. Okay? So a couple of simple examples, but you're going to hear solution, solute, solvent come back when we get to even the next chapter, which is actually going to be chapter 8 after this one. Okay, so it's really important that you understand these terms. All right, so make sure you have those examples jotted down. And as always, if there are questions about that, don't hesitate to let me know. Okay, the last thing we have to talk about is acids, bases, pH, and buffers. So let me see if I can get all the items up here that we need for this one. Okay, so you can see I've got a lot of vocab here on the left. Make sure that you get that vocab there, and let me just shift this down so you can see the bottom one there. All right, so an acid by definition, and if, by the way, if you've never seen this before, this is what we call a pH scale. Okay, pH scale goes from 0 to 14. The higher up in terms of numbers that we get, you can see here, the more basic it becomes, the lower, the more acidic it becomes. And this has everything to do with those solutions that we just talked about. So one of the characteristics we can use to identify a solution is on its level of pH. Is it an acidic solution, or is it a basic solution? So by definition, something that's acidic is something that will release H plus ions. So H plus ions are hydrogens that have essentially lost their one valence electron. In other words, they're essentially just a proton. Hydrogen atoms by themselves do not have neutrons in their nucleus. So when they're neutral in charge and they're not ions, they actually have one proton and one electron that's kind of circling that proton. Well, remember, it's not real content in that scenario. So if it's not going to share that electron, it tends to either give it away or it's going to pick one up. And more likely, it's going to give away the one that it's got. And when it loses that one electron, again, you're basically left with a single proton. So when we talk about hydrogens in the form of ions that have lost their valence electron, I tend to write them as H+, like that. Okay, so if you see that, that's what we're talking about, hydrogen ions. Acids, by definition, will release these hydrogens when they dissolve in water, and the amount of that hydrogen ion concentration in that solution is what determines its pH. Bases, on the other hand, do the opposite. So they don't push away and get rid of hydrogen ions. They actually will pick up and remove hydrogen ions from a solution. So the lower the amount of hydrogen ions, the higher the number on the pH scale, the more basic it becomes. Kind of complicated, right? A solution's acidity or hydrogen ion concentrations measured by our pH scale. So this right here, by the way, where I have these square brackets surrounding my H+, that means hydrogen ion concentration. So again, the amount of hydrogen ions in this solution. Okay, so when we look at our pH scale, like on the screen in front of you, where we have a low hydrogen ion concentration is actually going to be at the highest pH, right? So I could say here low hydrogen ion concentration, right? And here, as we get increasingly acidic, as we go from one end to the other, this is where we're going to have a higher hydrogen ion concentration. All right, so they're kind of inversely related, right? pH goes up, hydrogen ion concentration goes down. pH goes down, hydrogen ion concentration goes up. And again, that has everything to do with what these acids and bases are doing in a solution. Okay, so over here on the right-hand side, you can see I have some things, just general reminders. So a lower pH means that we have a solution that's acidic. A higher pH, we have a solution that is basic but has a lower concentration actually of hydrogen ions. There are some examples of different things here for which we know kind of a standard pH. So stomach acid tends to be down there about 1.5. It's very acidic. Lemon juice, orange juice, any type of citrus fruit tends to be around pH 2.5 or 3. Tomatoes, sodas, coffee all tend to kind of hover in this general vicinity right here. If you remember, we talked about acid rain that was around pH 5 or 4.5. Pure water is what we identify as neutral pH. So that's always pH 7. And human blood is slightly basic, actually. So we're a little bit on the other side of that pH, about 7.5. And then as we get further up this pH scale and get to larger numbers and higher pH, we end up with more, with stronger things like cleaners. So up here at the top is where we actually have bleach and toilet bowl cleaner and shower cleaner and all those things that if you've ever used them, you know they have a distinct kind of cleaning smell. And if you're exposed to them for too long, you're breathing in those fumes that can be pretty hazardous. Okay. So I don't need you to know the examples here that fit on this pH scale, but I certainly need you to know the examples of things that I jotted down here in boxes, right? If we have a low pH, it's acidic and there's a high amount of hydrogen. High pH is the opposite. And then certainly the vocab here on the left. But you certainly don't need to know where stomach acid is and where lemon juice is and so on. Those are just examples to give you some real world kind of things to relate to. Oh, and here's toothpaste down here, also basic, because again, it's one of those cleaner type objects. Okay, last one, buffer. Buffer by definition is something that binds with hydrogen ions when the hydrogen ion concentration increases, and then can do the opposite when the hydrogen ion concentration decreases. So buffers, essentially what they do is they help to maintain homeostasis in living things. They help to maintain a relatively neutral pH, or a pH at least within a range or a window that makes things operate the best, right? Most efficiently. So when we're adding buffers to things, like in a chemistry experiment, we're essentially kind of dumbing down the effects of those acids and bases, and we're allowing that pH to kind of maintain at a consistent level. So we do have compounds in our bodies naturally that help to do this process, similar to what we said earlier about water and how it maintains body temperature. We're talking about here buffers doing the same thing, maintaining a level of pH that's consistent with what our cells need to be able to function. Okay. So I would just know the definition for what a buffer is for this, and that should be it. So that is the end of 2.2 finally. So let me know if you have any questions. Otherwise, make sure you do the rest of the assignment. And I think I've got some videos I'm going to post separately with this one too. So other than that, take care, and I'll see y'all next time. Bye, y'all.